All right, guys. So we will start our first lecture on propulsion, and in that we will be starting with the topic which is jet propulsion. All right. So because this is the first lecture, let me set some ground rules. So anytime you people feel you have any doubt, any question, you can put the message in the chat. You can also ask me to unmute you and we can have the discussion. But keep one thing in mind, please don't move forward unless and until you are absolutely clear with the theory which I'm explaining. And in the process, we will start solving some practice questions also. Today, it will be more of theory because we just need to develop the equations first. All right, so please feel free. There is nothing like this is an bad doubt or this is very easy, I should not ask this. Nothing like this. Feel free, drop me a message in the chat, or if you want, ask me to unmute you and we can talk also. All right. Now, coming to the technical aspect straight away. So, let me first explain what propulsion syllabus is, because jet propulsion unit is very much relatable once you know the syllabus. All right, so we have discussed this in our introduction lecture, but I will go slightly more detailed now. So when we talk about our propulsion, right, we are talking something about 20 easily, and it can sometime go to 21, 22, 23, these number of marks. All right, so it is a heavy topic. Propulsion, out of all your 7 subjects, we have propulsion as a good amount of weightage. Now, in propulsion, you have 2 specific units. One is air breathing engines and one is non-air breathing engines. When we say non-air breathing engines, you will discuss everything about rocket propulsion here. So this is a separate unit. All right. Now, when it comes to air breathing engines, I will explain what do you mean by air breathing engines and all. You have 2 families. One is gas turbine engine family, which is part of our GATE syllabus. So this is what is very much required for our GATE. Second family, which is piston engine, is not part of our GATE syllabus. Right? In gas turbine engine, what we need to discuss are various kind of engines. So turbojet, turbofan, turboprop, turboshaft, ramjet, scramjet. There are all these kind of engines. So at least once we start propulsion, we should know what your whole propulsion syllabus will look like. So you will be talking everything related to these engines, rockets, and your gas turbine engine family. All right, now, before going into our first unit of jet propulsion, I'm still explaining you what do you mean or what is our GATE syllabus. So please listen to me carefully. The diagram, what you see here, right, is a typical cross-sectional view of a turbojet engine. All right. And in reality, it looks something like this. I will explain you each and everything. Now, I'm just taking an example to explain turbojet engine so that I can explain your syllabus completely, and then we will enter into jet propulsion, what we need to understand. So keep one thing in mind, any engine, turbojet, turbofan, turboprop, or whatever comes to your mind, the whole intention of those engines is to produce thrust in the forward direction. Correct? These engines should produce thrust in the forward direction so that your aircraft can move. And depending upon the power of the engine, you have fast moving aircraft, slow moving aircraft, and so on. And depending upon the speed, we decide which engine we should use. So you cannot use every aircraft with turbojet. You cannot use turbofan all the time. You cannot use turboprop. You cannot use turboshaft. You cannot use ramjet. So there is limitation, and there are many limitations. Not only speed, efficiencies, and then weight, cost. All these things come together to decide which engine we will be using in our aircraft. All right. Just a important note, whatever aircraft you typically see when you go to an airport, right? Typically, 90% of the aircraft you're going to see for commercial flights, you will be seeing turbofan engines mostly. 90% of the aircraft which are standing on our airports, right, are turbofan engines. And you will see why it is good for commercial aircrafts. Although turbofan will be used in fighter aircrafts also, and then very common fighter aircraft is turbojet also, and then we will see later where to use turboprop, where to use ramjet, scramjet, turbojet, turboshaft, and so on. So the final motive, as everyone agrees, is to make our aircraft move forward. And in the process, this engine has to do something so that it can produce thrust in the forward direction. Now, keep this in mind, thrust is kind of a force. All right, so it will be measured in newtons. Once this thrust is produced, your aircraft will move forward. Now, to produce this thrust, you need to do some physics, right? You need to produce some force. That means you have to do something in the system. Now, what is the basic gas turbine engine family basics or the backbone? How it works? It works like air enters inside the engine at some velocity Ci. Don't worry, I'm just explaining you the syllabus. We will go in detail of each and every word what I'm talking about. So this is the velocity with which air enters inside the engine. This is some low velocity, let's say 20 meter per second, 30 meter per second, or 50 meter per second, depending upon whether your aircraft is moving or not. If it is not moving, no velocity. Now, gas turbine engine family works on the basis of change in momentum. Now, what do you mean by this? The air which is entering at low velocity should exit the engine at very high velocity. C is the velocity term, and J we are saying is the jet velocity, or you can say C out also if you want. But CJ is a typical nomenclature followed in all the books. So at the entry you have low velocity, and at the exit you have very high velocity. And we will talk about mass flow rates in a bit. But because of this difference, right, between inlet and outlet, there is a force produced in the forward direction. Maybe you people have seen some movies also, right? Interstellar. Even in space, if you want to move forward, what you do is you fire an engine. It will produce huge amount of jet outside, and you will run forward. You must have seen this in some movies also. They typically use in cars for NOS, right? Additional thrust which they try to produce. You must have seen it somewhere. So whenever you want to move forward in this direction, you should give guesses outside at very high velocities. So that's the backbone of any gas turbine engine. So turbojet will work on this, turbofan will work on this, turboprop is a slight catch that we will discuss later. Similarly, shaft is a catch. Ramjet will work on this, and so on. So the idea is get very high velocity at the exit. Now, when you have low velocity at the entry and you want very high velocity at the exit so that you can produce thrust in the forward direction, you have to do something in between so that you can increase this velocity, right? And this, whatever red block I have given you, is your propulsion syllabus. To do that, we install few components, and you will understand. What you do, you install an intake. Don't worry what is the function, how it looks like. That is very detailed when we move forward. Then you install a compressor, which will compress the air. Then you will install a combustion chamber. Then you will install a turbine, which is this part. And then in the end, you have exhaust, which is also referred to as nozzle. Now, this sequence is for turbojet. But when I want you to explain the syllabus, right? So what is our gate syllabus? First, you need to understand a unit which is known as jet propulsion. Now, in jet propulsion, we typically understand each kind of engine, how it is built, how thrust is produced, how much efficiencies, how much fuel is burned, and so on. So we talk about complete engines when we talk about jet propulsion. This is our first unit, which we'll be starting now. Second unit is understanding in more detail about this compression process. Now, compression process is this process here. That means you're using a compressor, and there are two kind of compressors. One is axial flow compressor, and the third chapter is centrifugal flow compressor. So keep this in mind. These two are understanding in more detail how you will do a compression. Now, why compression is required, that we're going to discuss when we start our first unit. Then after this, we will understand how a turbine works. But in our syllabus, we only have axial flow turbine. We don't have radial turbines because it is not used in gas turbine engine family. You will understand this also shortly. So we understood about compression. We understood about turbine. Now, guys, please listen to me very, very, very carefully. This intake, this nozzle, and this combustion chamber is actually part of this unit. They are not separate chapters. So when we will start jet propulsion today, right, we will be talking about intake, we will be talking about nozzles, we will be talking about combustion chambers. Now, if you see, with the help of these four units, you have designed an engine, and you have designed turbojet, turbofan, ramjet, scramjet, any engine using these components. So you understood everything here. You understood how a compressor works. You understood how a turbine works, and if you combine them, you have entire gas turbine engine family ready. And that's what majorly your gate syllabus is. Now, apart from this, one last unit we're going to discuss is rocket propulsion, which is non-breathing engines. So it will have all separate physics, and depending upon that, we will decide what kind of rocket it is, how many stages it has, how much velocity it is producing, how much thrust it is producing. Separate thing. It's a complete different family. And to understand all this, you definitely need some basics, right? You should know what are thermodynamic laws. You should know what is internal energy, what is entropy. And again, I don't expect you people to know all this. So whatever is required, we will make sure that you people follow this in the lecture itself. So if you combine all this, right, this becomes your propulsion syllabus, which covers around 20 marks in your gate exam. All right. Now, there is not one book which is required, or like, but one absolute gem of a book, kind of a Bible for propulsion, is a book which is known as Sayyid Ahmad. If you people don't have it, it's okay. I will put this in a group. You should have a PDF of it. No need to purchase any hard copy books, not required, because you need to refer many, many, many different books. So Sayyid Ahmad, believe me, guys, it's a kind of a Bible for propulsion. It is equivalent to, like, we have John D. Anderson for aerodynamics, right? You have H.K. Das for maths. You have Megson for structures. Similarly, for propulsion, we have Sayyid Ahmad. But when we go into individual topics, right, I will be giving you advice for different books. Like jet propulsion, I'm just giving you an example. All these topics are brilliantly explained in Sayyid Ahmad, and believe me, many of the gate questions are simply copy pasted from this book. But we can read axial flow compressor, centrifugal flow compressor, axial flow turbine from other books like B. Ganeshan very easily. Indian author books, so English is also easy. Rocket propulsion can be read from John D. Anderson, Introduction to Flight, It can also be read from SM Yaya. It can also be read from Senthil. So there are multiple books which we need to refer. Similarly, Jet Propulsion is very good for turbojet and turbofan engine given in Cohen and Rogers. So don't worry about it. Once I'm going into the each topic, right, I will tell you which book to read if you people want. Otherwise, whatever study material books you people got, right, is a combination of all these good books in one book which you people have. All right. So what I suggest is, for now, understand the lecture, practice the questions with me, and later so refer your study material books. Then, if we want to go deeper and read more, right, then we will refer some separate books, which is my idea slightly in the next step. First, we want to understand the whole lecture. So, please give me a nod if you people are okay, understood absolutely what is your gate syllabus for propulsion. And if it's clear, then we will straight away start with our first unit of jet propulsion. Tell me, guys, please respond so that we can move forward. Great. Now, so you people understood your propulsion syllabus also. So I'll skip this slide. You know what is rocket propulsion. Now, if you see, we are starting jet propulsion now. That's our chapter 1. This chapter itself will go to around 6 marks. So you can imagine this is a heavy topic in your gate exam. All right. I told you in jet propulsion, we will be talking about different engines, right? You see, I've given an example so that I can make you people comfortable. If you see turbojet engine, just closely observe what are the components you have. You have an intake, you have a compressor, you have a combustion chamber, you have a turbine, and you have a nozzle. So you have 5 components there. Now, if you go to turbofan, you have a fan in place of intake, right? But if you see, there is a compressor, there is a combustion chamber, there is a turbine, there is a nozzle. So everything else remains same, but you have altogether different engine when you have installed a fan in front of it. But if you read everything about compressor, same compressor will be used here, same combustion chamber can be used, same turbine can be used, same nozzle can be used. The only difference is we have a fan here. Now, if you go to turboprop engine, you see, rather than using fan, which is inside the cover, you have used very big propeller blades which will be outside the engine cover. That's the main difference between turbofan and turboprop engines. But now, if you closely observe, same compressor, same burner means combustion chamber, same turbine, same nozzle. So, same components are used. But what we have done, we have changed one slight thing and we have a new engine itself ready for us. Another example, ramjet engine. So if you see, there is an inlet. Don't worry about this compression. This is not a combustion chamber. Sorry, this is not an axial flow or centrifugal flow compressor. This is basically compression coming from inlet. Don't worry about it. You have same combustion chamber, you have same nozzle, but if you see, there is no turbine. So if you add or remove component here and there, you end up with multiple different kind of engines, and all these engines comes under gas turbine engine family, and that's what we want to understand in jet propulsion. So what is our priority? Our priority is understand what each engine has, understand each individual component, and that's what all of your gate numericals. So from 2007 till 2026, the gate numericals will revolve around whatever I have said. The only thing is we just need to practice, we need to understand the equations, and we need to understand each and every engine in detail. Now, I have written detailed jet propulsion syllabus. Keep this in mind, this is our chapter 1. All right. So what we will be doing here, we will be specifically, as per our GATE syllabus, we'll try to understand inlet. I told you this is inlet. This is also known as intake. We will understand about nozzles. All right. We will understand about combustion chamber. I told you, right? Jet propulsion is a big unit. That's the reason it covers 6 to 8 marks in your GATE exam. Compressor is a separate chapter. Turbine is a separate chapter. But we will discuss inlet, nozzle, combustion chamber here itself. Then, if you see, you will talk about all the engines: turbojet, turbofan, ramjet, turboprop. We will also discuss turbo shaft and scramjet, although this is not part of our heavy GATE syllabus. There is one theory question asked in scramjet, but we will discuss about the theory. And then, once you have all the engines ready, you will discuss how much thrust your engine is producing, because in the end, you want to produce thrust, right? What is the efficiency of the engine? Is it very expensive to run it? Is it cost effective? How much fuel consumption is happening? And then you need to optimize your engines, right? Because in the end, you will sell this to companies, right? GE will develop an engine and give it to Airbus so that you can form an aircraft. So everything in the end is business, right? So you need to optimize. This thrust augmentation is nothing but typically used for fighter aircrafts, afterburners, when you want to produce thrust very fast and huge amount of thrust. And then this is part of your combustion chamber only, the chemical equations. So it looks very big, but what I will be doing is I will be looking into this every time we finish a chapter. We'll see what things we have covered. I have already written for this particular unit. You can follow Owen and Rogers, but the thing is, it will only give you turbojet and turbofan, and all propulsion will be given by this book, Sayyed and Ahmed, which is a must-have book for you people. Have it with you. If you have time, read it. There is no harm in reading books, but that is last step. First, you need to refer to the lectures and refer the study material, and then practice test series questions. All right. I hope I'm clear. Let's start with the first thing. So, how this thrust is being produced? Anyhow, you need to produce thrust to move forward, right? Now, I'll give you one very simple but very powerful insight. Just 1 second. All right. Now, you know, as per thermodynamics, first law, energy is conserved. All right. Energy can neither be created nor be destroyed, but the only thing you can do is you can transform it. Everyone knows this. All right. So if you have your engine, which you will be installing in your aircraft, and if this engine need to produce some kind of force, that is thrust to move forward, it cannot simply produce the force by just standing. You have to do or give some energy. So what we will do in our engines, the only input we give to our engines is fuel. Fuel, you know, has energy. So when you burn your fuel here, burning this fuel, which you are supplying it from outside, will generate energy. But the thing is that energy is heat energy. We know energy can neither be created nor be destroyed. So you are giving energy source from outside. The more fuel you're going to give into the system, more heat energy you're going to get. So as simple as that. So if you burn more fuel, definitely more cost, right? More cost, more weight. And the same concept works with everything in the world. You talk about cars, the only input you are giving is fuel, right? Either diesel or petrol engines. Now you are coming to EV. So some input you have to give. Everything comes with a cost, right? So you give some energy into the system and then you utilize that energy for your work. That energy here is fuel, and now you want to utilize this energy to move forward. As simple as that. And everything in world work like this. That's how God has created everything. So if you want to do anything, you want to sit and attend the lecture, you have to give food as the energy input to your body, to your mind. Otherwise, you cannot do anything. You cannot go to college, you cannot attend classes, you cannot prepare for anything, you cannot walk, you cannot play, you cannot do anything. So you have to give as an input. So this is the only input to an aircraft from outside world. But the problem is we don't want high temperatures. Heat energy means you are burning fuel high temperatures. Your intention is not to produce high temperatures. What you want to produce thrust. How thrust is produced? I told you at the inlet, your velocity is very low, and at the outlet, your velocity is very high. And this change in momentum will give you a push, a kick in the forward direction. So, what is our engineering mind says now? Our engineering mind says we have given the energy of fuel, we have burned it, we have produced heat energy. Now we should convert this heat energy into this high velocity, right? So we have to convert this maybe into high kinetic energy. So we have to do some conversions now. And to do that conversion properly, so that you have this high value of Cj, you do it with individual components. So you install an intake, you install a compressor, you install a combustion chamber, you install a turbine, you install a nozzle, just to do this conversion properly. Because if everyone works properly, you have high CJ, you have high thrust, and your aircraft happily flies. So this is the reason thermodynamic basics are required. If you know, it's okay. If not, but keep one thing in mind: thermodynamic first law simply states energy can neither be created nor be destroyed, and we are following that. Now, this is more of an verbal explanation. Let's go technical now. All right. So I will be following some notations, and I will not break this notation till the end of the year. Never, because this will be very common in all the books also. All right. Please listen to me carefully. Any engine, whatever engine you have, we have at the entry typically given as station number A. So anyone who is standing at the entry of the engine, any air is denoted as A. A basically denotes ambient conditions. The air is coming from atmosphere, right? When your aircraft is flying at, let's say, 11-kilometer altitude, so ambient conditions is represented as A. Don't worry, you can represent this as I also. You can represent this as 1 also. It's up to you. So at this, air enters, which is denoted as M dot A. Now keep this in mind. This is mass flow rate of air. Which is entering inside the engine, and its unit is basically kg per second. So if, let's say, as an example, in your gate numerical, the question is mass flow rate of air is 200 kg per second. So understand the meaning. This says every second 200 kg of air will enter inside this engine. You can imagine how bigger the number is. Similarly, it can be 50 kg per second. So it tells you how much air is entering inside the engine every second. And this is the reason they are air breathing engines, right? Air is entering inside the engine. Now, this air has to enter with certain velocity, right? and we will denote this as CI. Now again, don't worry, in many books, you will find this as CA also. You will find as CI also. I means inlet. Inlet velocity of air which is entering inside the engine. Right? Now this air will have some pressure also, right? Now don't worry about static pressure, stagnation pressure. That we will discuss when we discuss isentropic flows. As of now, the intention is to understand thrust equation. All right, and there are more than 15 questions in your GATE exam only on calculation of thrust. It's a common question repetitively every year. So don't think we are forming basics. We have actually started with your proper GATE syllabus. So this is most common numerical asked in your GATE exam for calculating thrust. All right. Now this PA represents the pressure of air which is entering inside the engine. Now keep this in mind. This pressure is totally and totally dependent upon where your aircraft is flying. Your aircraft will be flying at sea level. Then you know your pressure will be something else. If your aircraft is flying at, let's say, altitude of 11 kilometers, then your PA will be different because as the altitude goes, pressure will drop. Again, I don't expect you people to know this. We will discuss this, how the pressure varies. You have atmosphere also in your syllabus. So you enter with a pressure of PA, velocity CI, mass flow rate M dot A, and then your engine, depending upon what kind of engine you have, whether it is turbojet, turbofan, turboprop, turboshaft, ramjet, scramjet, any engine, whatever equation I'm developing now is valid for that engine. All right. So any engine, I'm not giving you that this equation is valid only for this engine. Whatever we are doing now is valid for all the gas turbine engine family. You do something inside the engine, we don't know what something is happening, but at the exit, you have high velocity. So this is our exit plane. So gases are coming out. Now, if you listen to me very carefully, right? I'm saying air entering and I'm saying gas is leaving. Can anyone tell me why this differentiation I'm doing? I'm saying air is entering, but I'm saying gases are leaving. Can anyone tell me why? Because you have burned air and fuel together, right? So you have burned it and the gases are being produced. Yes. Fuel is added and burned. All right. So now these gases, and don't forget, guys, you have added fuel here. Again, m dot f is mass flow rate of fuel. Now, if mass flow rate of fuel is, let's say, 2 kg per second, so every second you are adding 2 kg of fuel because you need to add it from outside, right? So, air plus fuel, gases are coming out at a velocity of Cj, and definitely these gases will be coming out at certain pressure, right? Let's say that pressure is PE. Listen to me very carefully. I'm going into a very important and advanced topic. So gases are coming out at a pressure of PE. They entered at a pressure of PA. And at the exit, you must be having some area, right? Definitely you must be having an inlet area also. But don't worry about it. I'll tell you how to utilize it. As of now, exit area is super important. Now, if you see, this area is reducing, right? And there is a basic theory behind it. I hope you people have used water hoses, right? Pipes in your garden or in your childhood, somewhere you have used it. Just tell me, guys, when you want to increase the velocity of water, what you will do? Is it not that you people slightly reduce the area of the outlet of the pipe? Guys, yes or no? You people do that, right? That is what we are trying to develop here. So if you see, your area is reducing, right? Now again, this is not that simple here, because you will be using some convergent divergent nozzles also, but in propulsion we will not going to discuss that. That is part of your gas dynamics syllabus. So as of now, don't worry, you have some exit area which is important for calculating your thrust. So gases are coming out at a velocity of Cj, pressure Pe, the area is Ae, and now we need to develop our thrust equation. And the equation which I am writing now is valid for all gas turbine engine family. That means you can apply it for turbojet, turbofan, ramjet, scramjet, whatever engine is present in your syllabus. So thrust I'll be representing as F, which is nothing but your force. And I'll give you one equation, then I'll explain each and every word very slowly for it. So your thrust equation, without any assumption, will look something like this. All right. Now, I know this is a complicated equation. It looks complicated. On this equation itself, I told you there are more than 15 questions asked in your exam, and this is directly a 2-mark question. All right. It looks complicated, but it is not. Understand few terms now with me. First, this term, what you see, right, is known as momentum thrust. So this thrust is coming because of momentum change. Now, what is momentum? Momentum is some mass flow rate into velocity. Mass flow rate into velocity is momentum. And we are talking about momentum change. I will explain that shortly. And the next thrust component is nothing but your pressure thrust. So there are two thrust components. One is momentum, one is pressure. If you add this, you will get your total thrust developed by the engine. Now let's understand each and every term here. So you people know what is m dot a. All right, guys, I'm doing very little maths here. So what is this F? This F is known as fuel-air ratio. And this F is basically the ratio of amount of fuel divided by amount of air. Nothing fancy. How much fuel you are burning and how much air is entering. That defines your fuel-air ratio. And it's a very small number, typically 0.02, 0.03, very small numbers. Because air entering will be very high and fuel burning will be very low. Now, if I substitute this value here, right? Now, this is only for your understanding. This equation, anything which I'm going to block while I'm taking the lecture, that means you people need to learn that equation. Now, next is understanding it. So what I'm doing is, I'm simply writing this F here. F is this, right? Into Cj minus Ci. And then you have your pressure thrust, pressure and area. It's fine. Now what I'll do is, I'll multiply this m dot a inside this bracket. All right, now let's do it together. When you multiply this m dot a inside, this first term becomes m dot a. If you multiply with this term, m dot a and m dot a got cancelled out and you get this. And this is multiplied with Cj. You can check this term is multiplied with Cj. And to that, we have multiplied m dot a. And then when you multiply this m dot a here with Ci, you get this term, right? Plus Pe minus Pa into exit area. Don't worry about this. This is our pressure thrust. We'll understand this later. As of now, you understand what is your momentum thrust. Your momentum thrust, if you read it closely, this is momentum at the exit. I told you what is momentum, right? Mass flow rate into velocity. So when you have your gases, these gases are coming out, and these gases will be m dot A plus m dot F, right? Because air and fuel are added. So outlet momentum is mass flow rate into velocity. Velocity with which you are coming out is Cj. So this is exit momentum minus inlet momentum. But in books, you will find this term, inlet momentum drag. Now, why the word drag? Because there is a negative sign. It stops you. I will explain you the physics later. Let's understand the equation first. So, change in momentum is giving you your momentum thrust. And change is exit minus inlet. And just for your understanding, I have opened this term, but now I hope you people understood why I asked you to block this, because this is very advantageous equation, right? This is what is known as momentum thrust. Now, what is pressure thrust? The pressure thrust is coming, now you know pressure multiplied by area is force, right? Correct? Pressure multiplied by area is force. Area is nothing but the area with which your gases are coming out. Alright? So, area of the exit, area of your nozzle at the exit. Now, if you see your gases are coming out at a pressure of PE, this is where the pressure is PE of the gases which are coming out. But you people know, and you can imagine this also, all the gases which are coming out go into atmosphere again, right? Because you are flying in air, atmospheric conditions. So gases are coming out at a pressure PE, and they have to go to atmosphere and go and mix with them. This pressure difference, PE minus PA, pressure multiplied by area, gives you what is known as pressure thrust. And that's very easy to digest. So the total thrust of your gas turbine engine family consists of two portions: momentum thrust, pressure thrust. Pressure is simply pressure into area. Momentum thrust is nothing but change in exit momentum minus change in inlet momentum. Now you know each and every word here. You know what is m dot A. You know what is fuel air ratio. You know this is velocity at the exit. You know this is velocity at the entry. This is pressure at the exit. This is your atmospheric pressure. And this is your nozzle area at the exit. And if you solve numericals on this, you will get your thrust produced in newtons. And they can ask in your exam, tell us in kilonewton and blah and blah and blah. That we're going to see shortly. Tell me, guys, are you people with me up till now? Any question? This is your time, guys. Let's discuss it. Absolutely clear? No confusion? Perfect. Okay. Now, this is, I told you, without any assumptions. So, whatever you feel, any numerical, the worst case, this is how the thrust is calculated. But in your gate numericals, they will try to update these things. As per the numerical, we have to pick our equation. Now, the next assumption they typically say in your exams, if fuel air ratio is very less than 1. Now, what do you mean by this? They will use the word fuel is neglected. Believe me, 80% of your gate numericals neglected. So if fuel is neglected, that means m dot f is very low. And if m dot f is very low, you can imagine if m dot f is very low, this value will be very small, right? So let's say this value is, I'm just giving you an example again. Let's say this value is 0.01, just as an example. So if you go to this equation, you have 1 plus 0.01 neglected. 1 or 1.01, it hardly create any difference, right? So if fuel added is very less, then you can neglect this F value, and then the thrust equation you should use in your gate exams will become something like this. You can imagine F is neglected, means this is gone. So you have only one. So your equation becomes m dot A into Cj minus Ci, which is your momentum thrust now, and your pressure thrust is Pe minus Pa into exit area. This is another form. People feel that there are so many equations we need to learn, but if you understand the concept, right, this is not a very big thing to learn. I hope this is very clear and makes sense. This is one kind of, so numericals are asked on this. Numericals are asked on this as well. And the third case is, please listen to me very carefully, very carefully, and we need to understand this concept very properly in nozzles. If your pressure of gases which are coming out from the engine, you know, PE is the pressure of gases which are coming out, is exactly same as atmospheric conditions. Guys, do you people feel this is good or bad? I'm saying the pressure of the gases which are coming out is same as atmospheric conditions. Is this a good case or a bad case, guys? What do you people feel? And I want you people to respond on this. Okay, Navya says it is good. Rudresh saying it's bad. Madhu says it's bad. Okay. Arins bad. Akash bad. Sneha bad. Alicia bad. Rajeshwari bad. Sonika says it's good. Shakti is saying choking. Okay. RN is saying pressure thrust is not. So there is some confusion. I understood why you people are saying bad, and I understood also some people why they are saying good. Now please understand first. This PE equals to PA. That means your engine is working in such a way that the gases are coming out of pressure exactly as PA. That means it is very easy for them to come out and merge with these people because they are kind of the same pressure, right? Now, there we will talk about when this pressure is very high, then this pressure, then what will happen? And if this pressure is very low compared to PA, what will happen? We will discuss it. It was referred to as over expansion and under expansion. Now, I don't want to complicate this in the first lecture itself. But when the pressure at the exit and atmospheric conditions are same, it is referred to as optimum expansion. That means it is best for your gases and go into the atmospheres without any problem. But there is one thing which happens here. We are using the word optimum, and the word optimum typically strikes in our mind that it is good, right? But the people mindset is if you substitute PE and PA as same, this thrust becomes zero. So the only thrust we have now will be this expression. So for optimum expansion case, thrust is equals to only this thrust, and your pressure thrust goes to zero. And this is the reason almost every one of you has responded that this is a bad case. But now I want you people to understand this is the best case. And in this case, the thrust produced is maximum. So at least one misconception is removed that pressure thrust is zero, so your thrust is less, and that is the reason it is bad, low. Now the question arises, sir, how you are saying when one term goes to zero, how you are saying this thrust is maximum? Now keep one thing in mind. This term is not same in both this term is not same in both the cases. When you have optimum expansion, the velocity at the exit will be is at its highest. You will get the best exit velocity. Now, why it is that we need to understand by understanding the concept of nozzle, and you will understand what is choking and unchoked nozzle. So slowly we will develop our concepts, but now the intention is please at least keep this in mind, and I hope you will remember this throughout your life because explanations and concept clear you will never forget. If you learn something, then you will forget, right? You're not mugging anything. I'm again repeating this. Even though pressure thrust is zero, still it is the best case because when you have optimum expansion, the velocity at the exit goes to its very high value. And when this exit velocity is higher, this momentum thrust is very high. I'll give you an example. Let's say in this case, this value is 10 and this value is, let's say, 2. So your total thrust in this came out to be 12. Again, these numbers are only for your understanding. All right. Now, and this is PE is not equals to PA. But when you have optimum expansion, this pressure thrust goes to zero, but this momentum thrust increased because of this high CJ at the exit. And why this CJ is high? Because of this person, because this physics is happening. And now if you calculate your total thrust, you can see this thrust is more than this thrust, right? Even though a layman person will think this term goes to zero, so definitely it is a bad case. But unknowingly, when this thing was happening, right, this CJ was increasing to very high value, and hence eventually what you see, this becomes a best case. So as an engineer, when you will start working in GE, Pratt Whitney, Rolls Royce, anywhere, right? Everyone wants to operate under optimum pressure conditions, but it is not always possible. It is very difficult to maintain that. And hence, in your gate numericals, you will find numericals on this equation, this equation, this equation, and depending upon the numerical, we will pick the equation. What data is provided, what data is, and then I'll pick the equation. Tell me, guys, are we good? Is my every word what I've said is clear to everyone? Excellent. All right. Now, just to make you people feel good, I really don't know whether I have kept any of the gate numerical here. I think I have not in this PPT. So I will pick some other PPT later. No, in this PPT, I have not kept it. It is more of understanding the engines. It's okay. Anyhow, we'll solve the numericals together. So keep one thing in mind. We will be solving every gate numerical from 2007 to 2026 in the class itself. All right. And that will same will be uploaded in your video portal also on the same day. So don't worry about it. You have these contents and you can always ask your doubts also anytime in group. So, sir, we can consider optimum case and an ideal case. Yes, this is an ideal case. I will come to that, Felicia. I will explain that also. Let me explain this to you. All right. Now, for that, okay, Felicia asked, sir, why CJ is increasing with PE equals to PA? All right. Now, please don't worry about this heading. It's an excellent doubt. I wanted to explain it before, but let's discuss it now. Again, I will be using some numbers to explain. So let's say atmospheric pressure is 1 bar. I'm not writing any unit. because numbers are okay. So here also your atmospheric pressure is 1 because you are flying in atmospheric conditions, right? Now, Helisha and other people also, I want you people to respond on this. Your air enters with some velocity. Let's take an example again, 100 meter per second. All right, so your velocity is 100 meter per second, pressure is 1 bar, and you entered inside the engine. The first component, what you see here, let's say it's a turbojet engine, is an intake. Now, I have not explained to you what is function of an intake, so please don't worry about it. But something will happen. Ideally speaking, this pressure value, pressure here, will increase. Please don't worry about it. Take my word for now. The next topic we're going to discuss is intake only. Why this pressure is increased from 1 to 5 and how it is increased. That's the main function of an intake. We will discuss that. But it will increase. Then you have your next component, which is known as your compressor. Now, the name itself suggests compressor. It will compress the air, increase the pressure. So, if you go here, this is increased to 20. So, pressure at the entry was 1. It is increased to 5 and then it is increased to 20. So, intake is doing something, compressor is doing something, and they have increased the pressure. Now, the third component, what you have is your combustion chamber. Now, in combustion chamber, we don't want to increase or decrease any pressure. So, what we're going to do? We're simply going to add fuel and burn it. Guys, this is known as heat addition at constant pressure. Why constant pressure? You don't want to change your pressure inside combustion chamber. Not required. We have already increased it. So heat addition at constant pressure. Can anyone tell me which thermodynamic cycle is this? If you know, it's okay. If not, it's perfectly fine. So in thermodynamics, there are various cycles. There is Carnot, Otto cycle, diesel cycle. This cycle is known as Brayton cycle. Perfect, Sneha. And this heat addition at constant pressure is known as an isobaric process. Now, again, I don't expect you people to know this, but because Helisha asked this doubt, so I'm explaining this concept because everything should be clear when I'll wrap up a lecture, right? So you're adding heat at constant pressure. And in thermodynamics, we name this cycle as Brayton cycle. So all your gas turbine engine, turbojet, turbofan, turboprop, ramjet, scramjet, all works on Brayton cycle. That means heat addition at constant pressure. Now, in simple words, let's say your pressure at the exit is 20. Although, guys, this is not true. This will be very high value because of heat addition. Now, why we say constant pressure, you will understand stagnation pressure will be same. Now, please, my intention is not to confuse you people. So if you see my actual heading, right, without the doubt, I would have explained what is the difference between static and dynamic properties and what is isentropic process. But because Helisha asked this, it's a very good question, so I want to explain. Please understand this pressure 20 to 50 is increasing because you are adding heat. And heat increases temperature and temperature increases pressure. But as an all, you have 50. Now, next component, what you have here is a turbine. Now, turbine is an exact opposite to compressor. Compressor increases pressures, turbine reduces pressure. So it reduces the pressure to, let's say, 30. Just take an example. Don't forget, you in reality started with 1. And because of your engine components, you have increased it to 5, increased it to 20, increased it to 50, and then again reduced it to 30. And then the last component, what you have is your nozzle. Atmosphere is sitting at 1. Now, what is the function of a nozzle? A nozzle is any person whose main function is, I hope you people have heard about Bernoulli's equation, but you cannot apply your basic Bernoulli equation here because that is valid for incompressible flows. I'm not confusing you again. But any nozzle, the main function is reduce the pressure and increase the velocity. So what it does is it converts your pressure energy into kinetic energy. You know, energy can be converted from one form to another, right? And why you want to convert it? Guys, you want more thrust. Thrust means I want high CJ. What I will do with high pressure? I cannot do anything with high pressure. I want high velocity. So nozzle will eventually convert your high pressure to high energy. Now understand one thing. Let's say your pressure is 30 here. This nozzle, let's take an example, has converted your pressure to 1. So 30 to 1, it has reduced. Anything which reduces pressure will increase your velocity. So at the exit, let's take an example, your velocity is 1000. So when your pressure is reducing from 30 to 1, your velocity increases to 1000. And this, if you people agree, is an example of optimum case. Now, if in this case you calculate your thrust, it will be m dot a into Cj minus Ci. Let's say your thrust came out to be, I'm just giving you an example, let's say 900. Is this clear up till now for everyone? Helisha, is this clear? Do you understood the concept, what I have explained up till now? Everyone is with me? But now think about it. And this is super important, and hopefully this is answered. This will answer your question. Now, Helisha, let's say this nozzle was not doing its work properly. It is not an ideal case. It is not an optimum case. So it started with 30, but it reduces your pressure to 5. But now your pressure is 5, atmospheric is 1. This is not optimum expansion. So you have reduced your pressure from 30 to 5. And when any pressure is reducing, velocity will increase, right? Let's say in this case, our velocity at the exit is 500. Now, you understood why when you have optimum expansion, your velocity at the exit is so high that your thrust is 900. In this case, where you have PE equals to 5, not optimum case, this is optimum. In general case, if you use 500 Cj minus Ci plus your pressure thrust also, maybe you get 700. So even though pressure thrust is 0 here, because of this high velocity, your thrust is best. And I hope I have answered your question, Helisha. How Cj is increasing with PE equals to PA. Keep this in mind. Nozzle can only convert the energy. So if it converts 30 into 1, it gives you high velocity. But if it converts 30 into 5, it gives you less velocity. And we don't want less velocities. We want the best velocity at the exit so that we have the best optimum thrust coming from the engine. Give me a nod, guys. Are we absolutely clear? I hope your question is also answered, Shlok. Alicia, it is clear. Guys, give me a thumbs up if you people are with me. Okay. So then it is the case. So Shlok asked this question. Sir, then is it the case that in the optimum case, fuel is consumed completely? So keep one thing in mind. Fuel is in your hand. If you want it to burn 2 kg, you will be burning 2 kg. Keep this in mind. This is kg per second, right? Till the time you will going to keep on burning it, sending it, you will be producing thrust. So thrust has nothing to do with whether complete fuel is burnt or not. Every second you're burning, right? If you switch off the engine, your thrust is zero. You're not burning any fuel. If you switch on the engine, You're burning fuel, your thrust is produced, and you can move forward. Shlok, it's exactly similar to your car. If you're not moving, if you're standing, you switch off the engine, no fuel is burned, right? And then when you start the engine, accelerate, more fuel is burned. Clear? Perfect. Really, really, really good. So, guys, let's keep it till here. I don't want to give everything in one shot. Doesn't make sense to have everything in one shot. We will start slowly.